So now we're in the home stretch. One of the last topics for Calculus 1 is what do we do about bases that are not base e? Now base e is the native base for the logarithm. It's the native base for the exponential function. And up until now, we've really looked at the derivative using this natural base. We've looked at the derivative of only the natural log base e, and that was 1 over argument, and then of course times the chain rule. We've looked at the derivative of the exponential function e to the x. Turned out it was pretty easy. It is e to the x, again times the chain rule, of course. But I want to expand our horizons a little bit further so that we are capable of taking the derivative and integrating with bases that are not necessarily base e. Not every exponential function, not every logarithm uses base e. Some use base 2, for example. Memory in a computer uses base 2 because it's a binary system, ones and zeros, on and off. That's base 2, and that's why you'll find that memory comes in multiples of 2, 64 gigabytes, 128 gigabytes times 2, 256, 512. That's when you buy hard drives, for example. You'll notice that they're really expressed in base 2. That's also true for bacteria that like to divide in half and double. So you start with 1 bacteria, you divide, now you have 2. Now 2 of those divide, you have 4. And then those 4 divide, you have 8. That's also base 2. We also use base 10, and we also use base 1/2. I'll show you an example of using base 1/2 in a moment. But I do want to start with a definition of an exponential function using a base other than e. And because we understand the natural base so well, we understand the derivatives using the natural base and the integrals that create the natural log, for example, I'm going to try to relate an exponential written with a different base somehow to base e. And if I can do that, I think we'll be able to start looking at taking the derivatives and integrating, and it'll be a lot easier. So let's take a look at bases other than e. Now for an exponential function, it would look something like this. A to the x. The base is base a. And we could assign a to be any base. We can make it base e, but we'll make it base 2, for example, and then we have the function y equals 2 to the x. We could make a equal to 10, and we would have y equals 10 to the x. And we could even make it a half, and y would be equal to 1/2 to the x. Now, the most important thing about our base is that we do want our base to be positive. That makes it positive. We don't want a to be equal to 0, and we also don't want a to be equal to 1, because that's not an exponential function. 1 to the x is always equal to 1. So a may not be equal to 1. Otherwise, you truly don't have an exponential function. So a needs to be positive. A may not be equal to 1. Well, there is a way to define a to the x using the natural base, base e. And it looks something like this. So it can be related to e to the x, except there's this little correction factor in here, ln of a. Now, ln of a is a number like ln of 2. If it was a equals 2, base 2, ln of 2 it's just a number. It's 0.693. I want to prove to you that this relationship truly exists, and this relationship is what's going to aid us in understanding how to take the derivative of an exponential function that is not base e. Now, how do we know that these two are really equivalent to one another? Well, one way to figure that out would be to take the natural log of both sides. This is an equation, and if it really is equal, then we should be able to do whatever we want to both sides. I'm going to take the natural log of the left side, and I'm going to take the natural log of the right side. Now, let's see if this works, guys. If this equation is true, that this little ln of a shows up here, then this equation must also be true. Now that I have some natural logs out here on the equation line, I can take advantage of the properties of the natural log, which allow me to take exponents and drop them in front. Now, this exponent has to apply to the entire argument, the package a here, it does. So the x can be brought out front, and I do get the ln of a. This is not calculus. This is leveraging the properties of the natural log. Now this says ln of e, that's the base, raised to this power. That entire power can come down and drop in front of the other natural log. So this entire thing drops in front, and now we're left with the ln of e. Well, look what we got here. X times the ln of a, are you equal to, let's use the commutative rule here, x times the ln of a times the ln of e? Well, the ln of e is the natural log, the log base e of e. And if you translate logarithm into English, it says, what would I raise? So what would you raise a little e to get an e? I would raise an e to the 1 power to get an e. The ln of a, or log base e of e, is actually equal to 1. So is it true? Of course it is true. Look at that, the same on the left as we have on the right. And that would be a check mark. So it's certainly true, and that means that should we want to replace a base other than e, we can do so as follows. So I've proved to you that it does work, and it is correct, and it is basically a method of changing the base, in a sense. It's a change of base formula for exponentials. So normally we talk about change of base formula with regards to logarithms, and we will certainly be doing that as well. But this seems to be a change of base for exponentials, and it is. I'm going to call this a correction factor. It's kind of correcting or adjusting for this different base here. So base A turned into base E as long as that correction factor is in place. Okay. Now let's talk about the derivative. So what if I asked for the derivative of a to the x? Now remember, a can be anything you want, a for anything, 2 to the x, 3 to the x, 4 to the x. Well, apparently, that's the same as this derivative on this side over here, because these two are equivalent to one another. Now, this is a derivative we know about. The derivative of e raised to a power is e for easy. It simply is e raised to that power. The whole thing. So remember, we check off e for easy, and it's just the same darn thing. But wait, we need a derivative of the inner function. Now, you might think you need a product rule here, but you do not. I'm doing a chain rule right now, and you're saying, okay, I need a derivative of this argument right here, ln of a times x. ln of a times x. It seems like product rule, but it's not product rule. Because the ln of a is just a number. So if a were equal to 2, for example, the ln of 2 is 0.693, and what would happen over here is this would say 0.693 times x. ln of a is a constant multiple, like 5. So what's the derivative of 5x? Just 5. What's the derivative of ln of a times x? Just ln of a. So what you've discovered is the following. The derivative of a to the x is all of this down here, but wait a second. Does that look familiar? Right there. It is a to the x, actually. So this becomes a to the x multiplied by the natural log of a. I'm going to keep referring to this as a correction factor. So by having the ability to rewrite any base exponential into the natural base, that is a function we know about. We know the derivative of e raised to something is itself. And then, of course, run the chain rule. So I did that. Now, what I discovered is the following. Apparently, the derivative of any exponential function is simply itself, just like e to the x. See what we found? But there's a little correction factor right next to it, which will be just a number in the end, because it'll be the ln of a. It's a correction factor, I call it, for the correcting for the fact that we are not using the natural base. And don't forget your chain rule, just in case you need it. Very important to remember that. So let's do our first derivative of an exponential function. Let's just do 2 to the x. It turns out that the derivative of any exponential function with any base is itself. That makes life much easier. Now the fact is I checked off 2 to the x. It is 2 to the x, but recognize that this is base 2, so I need a correction factor, which would be the ln of 2. And then don't forget to multiply by your chain rule, which would be the derivative of x, which is 1. So this is going to be the ln of 2 times 2 to the x. I guess it sort of makes sense to put the number in front here, because this is a number. It's roughly 0.693. Now, an important thing to note, I would prefer this because that's the exact answer. Do not multiply 2 times 2 is 4, because those are arguments and they're very well protected and they don't multiply together. So be careful of that. Let's try another one. Let's do the derivative of 10 raised to the x squared power. Now, be certain that you have an exponential before you take advantage of this wonderfully easy derivative. Derivatives of exponentials are themselves pretty nice, and it works even for bases that aren't base e. So let's make sure that this is a true exponential. A true exponential has a nice solid foundation, a base that's constant raised to a variable power. Yes, indeed, this is an exponential. I would check it off and write that the derivative is simply itself. Multiplied by, well, while we're at the 10 here, recognize that this is not the natural base. This is a new base, base 10. We need a little correction factor that basically is correcting for the fact that it is not base e. And let's never forget that chain rule. So here's what I would write as my answer. I put maybe the 2x in front. The ln of 10, that can come next. And then 10 to the x squared. Now, we can do a little more with this. We can. Because if I rearrange this a little bit, I want you to notice that, you know, a natural log still possesses all of those magical properties, including the property that allows you to take numbers or multiples in front of your log and put them up here as exponents. Now, you could take as much or as little as you want. In this particular example, I'm only going to take the 2 up there. So a nice compact version of this answer is x times the natural log of 100 times 10 to the x squared. Now, I guess if you want to have numbers in front, that's normally what we do have. Natural log of 100 is just a number, and then we'll take the x and then the 10 to the x squared. This seems like a more logical approach to writing our final answer. This is just a number. Your calculator can reveal that number to you. And then we have our x and our 10 to the x squared. So recognize that the derivative of an exponential function isn't really that difficult. It is itself, just like the natural exponential function. We do get this one extra piece of the puzzle, though. I'm calling it a correction factor. So here's how I remember where the correction factor actually goes. Now, we can have base 1/2. As long as it's greater than 0 and not equal to 1, we can have a base 1/2. And I'd like you to take the derivative of 1/2, and why don't we do this? We'll put raise 1/2 to, how about something crazy here? How about the sine of x? Let's really mix it up a little bit. Now, is it an exponential function? Yes, it is. It's a nice, solid, constant base, not a variable, a constant base raised to a function of x. So we check it off, and we say that the derivative of the exponential function, easy, it's itself, and that makes life easier. Now, while we're here, let's also use this check mark to put that adjustment factor, which would be the natural log of 1/2. It's the natural log of the old base. It's just a number. And then finally finish up with the derivative of sine, which is cosine, and then, of course, the derivative of x, which is 1. So the answer here would be the following. Let's put cosine of x first. Usually we reserve the exponential for the very back of the problem. And let's put this number right here. Now, there's more to this number than meets the eye, because it's a logarithm that could be broken up as natural log of 1 minus the natural log of 2. But the natural log of 1 is 0. So here's another version. That's another good version of this problem. So remember this. The derivative of an exponential is pretty easy. It's the same as the derivative of e to the x, e for easy, but it's a different base. So that's the one last component that you need to put into your derivative, is that little correction factor, and it will always be the ln of the old base. Now, let's try not to lose sight of the fact that not all functions are exponentials. We may believe that to be the case, but we have to be careful. I know that you know this answer, and it's no big deal. But notice how different it is than this. It's a world of difference. And there it is again, the correction factor. Okay. So I encourage you to practice using the derivative of a base other than e, and simply by inserting the correction factor. So I guess the real question was, okay, now that I know there is a correction factor, where does it go? Now, for derivatives, it's fairly simple to know that. Let's do the sine of x cubed. Isn't it nice to know that the derivative of an exponential just is itself? So where does the correction factor go? The correction factor goes right where you just put your derivative. In this case, right next to it. So I'll say that again. You know the correction factor now, what it is. It is the ln of the old base. And it's from that equivalence that we learned where it was basically a change of base formula for exponentials. So where does that correction factor go? Well, with derivatives, just remember this. It goes right next to where you just placed the derivative. I just placed the derivative here. It is simply itself. Correction factor goes right next to it. Let's not forget our chain rule. Derivative of sine is cosine. No change to that argument. And one more derivative, that would be 3x squared. And so putting everything together, let's see what we got here. How about my x squared my cosine of x cubed, and then you can put your exponential back here. I tend to put the more complicated functions in the back, and you see how it gets more and more complicated. And then wait, we've forgotten to put down the ln of 5 and the 3. Okay, well, here's the 3, and here's the ln of 5. It's simply a number. In fact, it's this number, ln of 5 cubed. So yes, you can use the properties of logarithms, and that gives us a good answer here. And this would be a good version of the final answer. If you can, take that constant in front of the logarithm and put it up there as an exponent. Now, there's one example in the book here, example 1, in fact, of using a base other than base e for a non-calculus problem. And it's a good problem to know about. It's called the half-life problem. And radioactive material has what's called a half-life. Each radioactive material has a different half-life, and it's the amount of time that you would need to wait for that material to lose 50% of its radioactivity. So, for example, if you had 10 pounds of radioactive waste, let's say, you would have to wait a half-life, whatever that number is, in order for it to become 5 pounds. Now, you probably still have 10 pounds of material, but only 5 pounds of it, or half of it, is radioactive. So it's losing its radioactivity a half a unit at a time. So now for carbon-14, the half-life of carbon-14 carbon-14, I should comment, is a radioactive isotope of carbon. So we're primarily designed with carbon-12, which is your standard run-of-the-mill carbon atom. Carbon-14 is radioactive, slightly radioactive. Now, its half-life is rather long, and I've seen it quoted at different figures. Our book uses 5,715 years. That's a long time. So that means that because radioactive carbon is in the atmosphere, it's a very small percentage, so don't worry about it. It's not going to kill us, but very tiny percentage. Every time we're alive and replenishing our body with carbon, which we do all the time, we pick up a little of this carbon-14. Now, when you die, or when an animal dies, whatever carbon-14 is in their body is locked in. And let's say that was 1 gram. Now, we dig up the fossilized remains 5,715 years later, and we measure how much carbon-14 is in this particular fossil, and we read 1/2 a gram. So we can do the projection and say, well, based on the size of this animal, it should have had 1 gram while it was alive, and now it only has 1/2 gram of radioactive carbon. How did that happen? Through radioactive decay. So there's a great exponential equation that we use that looks something like this. So this is the original amount. This is the new amount. This is the half-life of the radioactive material, and this is basically the amount of time that you wait. And this particular problem certainly does not use base E. It uses base 1/2. So let's say that you did have 1 gram of radioactive carbon in a living animal at one point because of its size. And the half-life of carbon-14 is 5,715 years. Every 5,715 years, the amount of carbon-14 gets cut in half. So if you wait, I guess, 11,400 years, instead of 1 gram, you'll have 1/4 of a gram because you cut it in half twice. So I'd like to know how much carbon-14 would we have in, oh, I don't know, about 15,000 years. Now, if you look at this, 15,000 years is about 3 half-lives. So if you want to project how much you would have, you would start with 1 gram. 1 half-life has expired, so cut that in half. Now we're up to a half a gram. But a second half-life has expired, so we cut that in half. Now we're down to a quarter gram, and then finally a third one has expired. We've gone through 3 half-lives of time. And so, you know, we should roughly have 1/8 of a gram. So let's run this formula through and see what we have. Now, the original amount would be 1 gram. I'm just showing you that we do use other bases other than E. We use a half as a perfect base for this. We should end up with about 0.125. Now, we allowed 15,000 years to go by. It is a unit of years. The half-life is 5,715 years. And so what we need to do now is take 1 gram, and you notice the units cancel. And there's no units for my base either. And I want to take that and raise it to the 15,000 divided by 5,715. So I'm working that out now, just so we can finish this. And like I said, it's about 3 half-lives, but it's actually 2.6247 basically, and it does go on for ever and ever. So guys, what we're going to do now is find out, do we really get about 0.125? So I am now taking my half, and I'm raising it to 15,000 divided by 5,715, which I said was about 2.612, equals, and we got about 0.162 grams left, which is not 0.125, but that's quite okay because we actually did not allow 3 full half-lives to go by. We only allowed 2 and about a half. So just a quick example, it's not calculus, just a quick example of where we do use bases other than base E. Okay, now, the next thing I'd like to look at is I want to look at the derivative of a logarithm that is not the natural log. Let's take a look at that. And for that, it's really handy to remember 2 things. Number 1, that the derivative of the natural log function is simply 1 over x. Now, if it's not just x, if it's a function of x, like u, you really do need your chain rule. So derivative, check it off, is 1 over argument. Derivative, check it off, is du dx. So don't forget your chain rule. That's all that is. I could do my chain rule here if I wanted. Derivative is 1 over x. Derivative of x is already there. It's 1. So let's not forget our chain rule. Now my question is, what's the derivative of some other log, like log base a? I'm talking log base 2, log base 10, log base a half. Now, base a, same rules apply. It's got to be positive. It can't be 1. All right, it's the same as our base that we use for our exponential. So let's pretend for the moment that we have no idea what the derivative of log base 7 is, okay? But we do know the derivative of natural log. The other property that's really important that you should know is the change of base property for logarithms. Isn't it true that you can change to any base you desire? And I prefer to change up to base e, and we'll put a log base e on the top and a log base e on the bottom. You take the log base e of the old argument, and you take the log base e of the old base. So that's just a property of logarithms. That's called change of base. We haven't done any calculus yet. Well, we don't need log base e. We know what that is. It's natural log. Now, at this moment, you might be thinking quotient rule, but the quotient rule isn't necessary. And let me explain to you why it's not necessary. The natural log of a that lives on the bottom is just a number. A is going to be a base like 2. And the ln of 2, which will be sitting down there, just says, I'm worth 0.693. I'm a constant down here. So we know that constant multiples can be dragged out in front of our derivative. We don't need to take the derivative of a constant multiple. What we do need to take the derivative of is a function of x, but that's a very familiar function of x, isn't it? That's the logarithm, the natural log. And we know the derivative of that. So this sits out here. We take the derivative of the natural log, which is 1 over argument. We take the derivative of x, which is already there, 1, and here's what we get. And here it is again, that correction factor. This is a pretty nice discovery, because now I know that the derivative of any logarithm is actually 1 over argument. So log base 2, log base 3, it doesn't really matter what base it is, because by using change of base, we can change any base into log base e, and that's a function we know about. The answer for that derivative is 1 over argument. Well, the bottom line is that you can now take the derivative of any base, like base 2. So here's how we take the derivative of a logarithm that is a base other than e. We now realize that the derivative of any log is 1 over argument. Now we look at base 2 down here and we check it off and we remember, yeah, we need one of these guys. They're called correction factors, or at least I call them correction factors. I'm correcting for the fact that this is not a natural base. It's a base 2. I need an ln of 2. And the question is, where do I put the ln of 2? Well, remember, when we did exponentials, I said put the correction factor right next to where you just placed the derivative. Well, look at where we just placed the derivative, right there. So put the correction factor next to it. Also, don't forget your chain rule. Derivative of x is right there is 1. So now technically, it is correct to do this if you want to. I don't have any problem with that. That tightens things up a little bit. We are allowed to push anything in front of a logarithm that's a multiple up as an exponent. So that's perfectly legitimate. If you want to do that, you can do that. There's nothing wrong with that. Okay, normally I don't seem to do that. I don't like pushing up those variables, but it's perfectly permissible to do that. So let's try another logarithmic derivative. Let's try log base 10. Derivative log base 10 of, how about x squared plus 1? Now the first thing you really want to think about is if you have the ability to leverage the properties of the log, I would leverage them first. Remember, we can move exponents out front. Do that first. Remember, we can separate logarithms. Multiplication on the inside becomes addition on the outside. Division on the inside becomes subtraction on the outside. I don't really have a good rule. For addition or subtraction inside. And that little squared does not apply to the whole package. So no, I can't move the 2 out front. So we're just going to take the derivative as you see it here, step by step. First of all, check off the log. Any log derivative now is known to be 1 over argument. Just like that. That's the argument right there. Check off the 10. It's the wrong base. We need a correction factor. Where does the correction factor go? Right next to where you just dropped the derivative. So it would be an ln of 10. It's just a number. And finally, chain rule, take the derivative of x squared plus 1, which would be 2x. So the answer here is 2x over ln of 10 times x squared plus 1. And the 2 and the ln of 10, they're just numbers. The variables are x and x squared plus 1. So I think you have a pretty good idea as to how to take the derivative of log base anything at this point. Same with exponentials. Okay, we can take the derivative of exponentials. The only difference is that each one of these will have a correction factor. And it's important to know where that correction factor goes. For derivatives, just remember, put the correction factor right where you just put your derivative. Now we're going to go a little further, and we're going to talk about integration. Now the only function I'm truly going to integrate here will be exponentials, because it's awfully hard to integrate and create logarithms that are not natural logarithms. Like, for example, number 1, it's a fraction. Number 2, the denominator is truly to the 1 power if you encompass this in parentheses. And number 3, yep, I made it so. The derivative of the bottom lives on the top. Don't forget your payoff. The payoff is it is a natural log of the denominator with the protection of an absolute value. Oh, but x squared plus 1 is always positive. It doesn't need the help of an absolute value, and I do want you to drop that if you can. So how do you integrate a problem so that it becomes log base 7, log base 8? We really don't do that. We don't. And if you want this natural log to be a log base 7 or log base 8, you can do that. So if you said integrate this problem and use log base 13, can you do that? Sure you can. Change of base. Right now, this is log base e of x squared plus 1. If I said provide the answer in base 13, you'd say, yeah, the only way to do that is change a base. That would be log base 13 of the top and log base 13 of the old base. I'm not going to ask you to do that, so don't worry about it. I won't ask you to integrate to a log base 13. Won't happen. But I'm just demonstrating that when I integrate fractions, it's pretty much unavoidable. I create natural logs every time. So what about integrating exponentials? Let's take a look at that. So I will ask you to integrate exponentials that are other than base e. But just as a little refresher, remember, the integral of e to the x, we love e to the x, is just e to the x because the derivative of e to the x is e to the x. So that works great. Uh-oh. What happened here? So that's a really good refresher. It's just not true that you can integrate e to the something and it simply becomes e to the something. We don't have permission to do that. We need the key or the permission that gives me the ability to do that. You know why? I can check my answer and I can see that it's wrong. Because the derivative of an exponential, oh, luckily, is itself. I get that part. But chain rule sticks a 2x over there. Where's the 2x over there? So this is not correct. In order to do this problem, there would have had to have been a 2x in place. Now, you could do this one of two ways. U-substitution is a great way to do it. U equals the argument, which is the x squared. Autopilot du dx. And look at how this problem ends up. E to the u. Box this up. Box it up. It's just, well, that turned out to be nice and easy. In fact, that's probably the easiest integral we have in calculus. That one I can do. Replace u with what it used to be. It was x squared. And now we have an answer. See, the 2x has to be there in order for me to get that answer. If I take the derivative of this, see, the 2x pops out, and we get that. So be careful. Be careful when you're integrating exponentials. So what do we do about this? Integrate 5 to the x power. Exponentials are really this easy. The antiderivative of the exponential usually is the exponential as long as the evidence or key is in place. Then that is the case. So the integral symbol's looking at this 5 saying 5 to the x, you are an exponential. I would love to write the answer 5 to the x, but I have to see if I've got permission to do that. Permission would be the derivative of the argument The derivative of x is 1, and there is a hidden 1 in here, so we're good to go on this. We can write 5 to the x on this. But wait, it's the wrong base. So there needs to be a correction factor somewhere, and you know what that correction factor is going to be. It's going to be the natural log of 5. The question is, where do I put it? Now, for a derivative, you remember the derivative of 5 to the x would be 5 to the x times the ln of 5. Remember, I said the derivative, the correction factor goes right next to the derivative, but this is not a derivative. This is an antiderivative. Everything is backwards. So the correction factor should actually end up down here. So when you integrate an exponential, it actually does behave like e to the x. It is itself. However, there is that small little correction factor. It's an ln of the old base, and the question is, where do I put it? Well, with derivatives, you put it next to the derivative. With antiderivatives, it's opposite, so it must go on the other side, in this case down below. Let me check that theory out. Is this true? This better be a nice clean 5 to the x. Let's check it out, guys. Now, ln of 5 is a number. I don't know what that number is off the top of my head, but it is a number, and it can slide out front. We don't have to do the quotient rule. We don't need to take the derivative of that. But we sure need to take the derivative of this. And I know I've altered my c a little bit. That's okay. It's just a constant. So 1 over ln of 5. Here we go. Derivative of an exponential is itself. We love exponentials. Oh, wrong base? No problem. I'll put a correction factor right here. And finally, the derivative of x is 1, and the derivative of a constant is 0, and everyone's happy. We got our original integrand back, 5 to the x. So that's how it works. Now I'd like to do a problem with U-substitution to see if we can really follow through on this. Here we go. Let's integrate 2 raised to the x squared multiplied by x dx. I can tell you that without that x, you really can't do this problem. We do need it there. Now, U-substitution, U equals inner, in this case the argument, which is the exponent, is a good choice for you. Autopilot. And this is working out quite nicely, because now, instead of x squared, I could do 2 to the u. Nice and, it's much cleaner that way. Box up what's left, go hunting for that box right here, and if you divide both sides by 2, you realize that x dx can be replaced with du over 2. The 1/2 slides out front, and in the end, all I'm asking you to do is integrate 2 to the u. Now the 1/2 is the survivor. Integrate 2 to the u is just 2 to the u. That's it. Oh, but it's the wrong base, so we need a correction factor. The correction factor will be the ln of the old base, ln of 2. Where does it go? Well, it used to go next to the derivative, but this is not a derivative. It's an antiderivative. Everything's backwards. It goes on the bottom. So here's a great version of this answer. In fact, I've got a couple versions that we could go with. Here's one version. See what I did there? I put these two together and I subtracted the exponents. Or here's another version. And see what I did there? I took this 2 and I plopped it up there. Isn't it amazing? They look entirely different, and yet they really embody the same answer. Now let's not forget what u actually is. It's x squared, which apparently is equal to this. Both answers are equivalent. Both answers are certainly acceptable. Now, as we've done a lot of U-substitution problems, I always call it guidelines. And think about the guidelines I provided you for U-sub. The most important one is U equals inner. And then, of course, always autopilot, take that derivative du dx. There was another guideline I provided you, and that was for fractions. If the denominator is to the 1 power, u equals denominator was a great guideline. Now for this problem, if you look at what I chose my u to be, I used the guidelines. I said u equals inner. And here's why I keep calling it guidelines and not a rule. Number one, it might not work. Number two, there might be another good choice for you that will get you the final answer. So I want to just demonstrate to you with this final problem that there is another choice of u that works. In fact, it's a really interesting choice for you. Let's try it. So u equals x squared, that seems like the most obvious choice. It kind of looks the same here. The box matches up, and you do get a relatively simple integral here that we can all perform. Do not add 1 to that exponent. This is an exponential whose answer is itself with the correction factor. But what if I tried this one alternative way? Now, this method is entirely different, but it's got to lead to the same result. What if you chose u to be the entire exponential? This whole thing right here. That goes against the grain a little bit. That's not really the guideline. The guideline would certainly be u equals x squared, and we met with success. But I'm trying to show you there are other ways to do the problem that will also be successful, and you might find this way rather interesting when it comes to exponentials. Now I want you to make sure that you're on autopilot here. So autopilot says, don't forget your derivative, du dx. Du dx is, okay, that's a derivative. We like derivatives. They're a little easier than integration. So we check off the exponential 2. It just is an exponential, so the answer is itself. We love those. While we're checking off the 2, remember the base is not base e, it's base 2. So we need one of these little correction factors, and of course it goes right next to the derivative. And finally check off the x squared, which is 2x. Now if we move the dx to the other side, which we often do, watch what happens. Du equals 2 to the x squared, the ln of 2, times 2x dx. These are just numbers, so I'm going to group them together in the front here. In fact, I might as well push this up as an exponent. We're allowed to do that. That would be 2 squared, right? Makes for an easier problem. It's kind of a simplified version. And now something very interesting happens. I need us to go back to the original problem here. Now normally what you end up doing is most people would say, okay, well this is u right here. This is u. Got it, the whole thing. And then you box up what's left and you say, well, what do I do with this? And here it is. But there's something even more interesting happening here. What if I just divide both sides of my derivative by the ln of 4? What do we learn by doing that? Watch what happens. Sorry, ln of 4. Isn't that crazy? The whole darn thing is a match. It's like I never even got in to put my u there. It's like the whole thing. Look at that. Okay then, I can replace that whole ugly box with du over the ln of 4. Now we know the ln of 4 is simply a constant multiple, and I'm really, really liking this integral right here. Isn't that crazy? That's a completely different way of doing business, and yet we're going to get the same answer. But look at how easy the integral really is. Integrate du, the integral and the u touch each other, the antiderivative and derivative, and we just get u over ln of 4 plus a constant. And what was u again? Well, let's scroll back to take a look here. I chose u to be the entire thing here, 2 to the x squared. Well, I think that was the answer when we did it the other way. Let's just double check that. Yeah, it's right here. Same exact answer that we got before. So there are multiple ways to do a problem like that. So I'll leave you with this. If you're taking the derivative of an exponential function, take the derivative the way you take the derivative of e to the x. E for easy. It just is itself times the chain rule times the correction factor. If you're taking the derivative of a logarithm, take the derivative as if you were taking the derivative of natural log. 1 over argument times the chain rule. But we need the correction factor, and it would go down below because you did 1 over argument. So the argument sat down there, the derivative sat down in the denominator. So that's where the correction factor goes. And then finally, when you integrate an exponential function that is a base other than e, you can use U-substitution. Apparently, you can use u equals the inner or u equals the whole exponential. Probably you'd be more comfortable and more familiar with u equals the exponent, just the exponent. And there should also be a correction factor. And where does that correction factor show up when you integrate? Down below. So thanks for your time today. I do encourage you to look at the homework problems. And don't forget that you're doing more than just taking the derivative of exponentials and logarithms. Sometimes we throw other things in there where you need a product rule or a quotient rule. So don't forget to be keeping in mind that, and especially the chain rule. Thanks, everyone.